In this video, I introduce DeepXplore, automated testing of autonomous driving models. DeepXplore is designed for systematically testing a self-driving model to find its incorrect behaviors. Suppose we have n pre-trained self-driving models, and all the models can predict the correct driving direction using the images in the training dataset as the input. Because a complete training dataset is infinity, the training dataset is used to train the models is just a subset and cannot cover all the driving scenarios. What we need to do now is use the DeepXplore to find the missing valid and realistic driving scenarios based on the images in the training dataset. To this end, first we fix the model parameters in all the self-driving models, and then try to find the relationship between the neuron coverage and the prediction with the input image. And then we define this relationship as the objective function. And then I use the gradient descent method to update this input image by adjusting the brightness of the image or adding a rectangle or some dirty spots in the input image to get the modified driving scenarios. And then we use this modified driving scenarios as input to the self-driving models. We hope at least one model to predict the wrong driving direction with a maximum neuron coverage. Here, we define neuron coverage by the activated neurons and all the neurons divided by all the neurons in the same neural network. Suppose we have input features in one feature map, and then we calculate the weight sum, and then use this weight sum as an input to the nonlinear activation function to generate the features in the next feature map. If a feature value V is larger than the threshold, that means this neuron is activated. To use a gradient descent method to update the input image, we need to define function f as an objective function. And then we calculate the gradient of the objective function f to get a gradient, and then we use this gradient to update the input image. What we need to do is to use this modified or update image to make this neuron coverage maximum and make the difference of the model prediction maximum. This means we need to find at least one self-driving model predicts the wrong driving direction. Here we use this difference to define the objective function 1. That means this is the prediction from all the models except the self-driving model G. And this is the result from the self-driving model G. What we need this model G predicts the wrong driving direction. That means we need to make this difference maximum. Consider objective function 2 to maximize the neuron coverage. We define the joint objective function, includes two parts. One is the difference maximum, one is the neuron coverage maximum. This is the balance factor. Here's code this objective function 1 and this objective function 2. And then now we get this joint objective function. Then we calculate the gradient of a joint objective function with respect to the input image. And then now we use this gradient in the constraint by adjusting the brightness of the image, or by adding a rectangle or some dirty spot in the image. And then now we get this update this new image. We use this update or modify the image as the input to all the self-driving models. If a current model predicts the result different from other models, that means we already find the incorrect behavior with the maximum neuron coverage. Here is the examples. If we pick images from the training data set, this is three, and this is all the three self-driving models can predict the correct driving direction. That's no problem at all. However, if we adjust the brightness of the image, make this lighter or darker, or we add a rectangle here, here, or here, or we add dirty spots in the image, we found at least one model predicts the wrong driving direction. Here is section one, wrong driving direction. For more details, please check with this reference. Thank you. Bye.